There's a black hole the size of 10 million suns tearing through empty space right now at 2.2 million miles per hour. It has no home, it has no galaxy, and behind it, stretching across 200,000 light years of dark intergalactic space, twice the width of the entire Milky Way, it is dragging a glowing trail of brand new stars that have no business existing. When astronomers first saw it, some of them thought their instruments were broken. Because what this object is doing breaks one of the most fundamental rules we thought we understood about black holes. A black hole is supposed to destroy matter. It is supposed to consume, crush, and swallow everything around it. So why is this one out in the cold? Dead middle of nowhere, moving faster than anything its size should be able to move, creating stars? And more unsettling still, what force in this universe is powerful enough to throw something that massive out of its own galaxy in the first place? That question was just answered. The physics was just published. And the answer changes more than what we know about black holes. It changes what we know about how many of these things might be out there right now, invisible, sailing through the dark between galaxies, completely undetectable. This is the full story. It started the way the best discoveries always do, by accident. In 2023, a team at Yale University led by Peter Van Dockum was going through old Hubble Space Telescope images, not looking for black holes, not looking for anything unusual. They were cataloging star clusters in a completely unrelated dwarf galaxy. Routine archival work, the kind of thing scientists do constantly when mining old telescope data for things the original observations were not designed to find. And then someone saw something that had no right to be there. A streak. A thin, perfectly straight line of light drawn across the darkness, pointing like an arrow at a distant galaxy system roughly 8.8 billion light years from Earth. The first assumption was a cosmic ray, a charged particle hitting the camera sensor and leaving a scratch across the frame. This happens constantly in space. The standard check is simple. You look at the other exposures of the same patch of sky. If the streak is gone in the next image, it was a cosmic ray. You discard it and move on. This one did not disappear. In every exposure of that same region, in exactly the same location, the streak was still there. Real, persistent, pointing at the same galaxy. And that was the problem, because straight lines spiral, gas clouds scatter, plasma jets fired from black holes curve and spread. Nothing in the universe draws a clean, perfectly straight 200,000 light-year line across a void. Nothing except something massive moving in a single direction at enormous speed for an enormous amount of time. One by one, the ordinary explanations failed. Edge and galaxy, wrong light profile. Plasma jet, wrong geometry. Cosmic ray, repeats across exposures. The strange explanation kept surviving. A supermassive black hole somehow ejected from its home galaxy, tearing through intergalactic space, building a wake of newborn stars behind it. This had been a theoretical prediction for over 50 years. Since the 1970s, physicists had calculated on paper that galaxy mergers could produce the conditions needed to launch a supermassive black hole out of its host. But in half a century of astronomical observation, nobody had ever found direct evidence it had actually happened. The prediction sat in textbooks, labeled theoretically possible, and mostly forgotten. Now something that looked exactly like a runaway supermassive black hole was sitting in Hubble archival data, pointing at a galaxy system nearly 9 billion light-years away. Hubble had shown them the streak was real. What they needed next was a telescope capable of measuring what was actually happening at its leading edge. They pointed James Webb's NIR-SPEC instrument at the tip of the streak. NIR-SPEC does not just photograph. It breaks light into its component wavelengths and reads the chemistry and velocity of whatever produced it simultaneously. The data that came back was unambiguous. The site index from 44 to 1. At the leading edge of the streak, the researchers measured a dramatic, abrupt velocity difference. The material behind the shock front is moving 600 kilometers per second, faster than the material in front of it. 600 kilometers per second of velocity change packed into an extraordinarily small region of space. That kind of sharp, localized velocity spike has exactly one explanation in physics. Something massive moving through that gas at supersonic speed, slamming into it and compressing it into a wall. The shape of the shock, the temperature of the gas, the geometry of the whole structure, all of it pointed to the same conclusion. Site index 44/1. This overall structure can only be created by a high-speed, massive object surging ahead at around 954 kilometers per second. The James Webb Space Telescope had just confirmed the first runaway supermassive black hole ever found in the history of astronomy. Scientists designated it RBH1, Runaway Black Hole 1, because the expectation now is that this will not be the last. Let that velocity sit for a moment. 954 kilometers per second. That is 2.2 million miles per hour. 3,000 times the speed of sound at sea level on Earth. At that speed, this object could travel from Earth to the Moon in 14 minutes. It could cross the entire width of our solar system in a few days, and it has been moving at this speed, unchanged, for approximately 70 million years based on the length of the star trail it has built behind it. Now here is the part that stopped researchers cold when they first understood what they were looking at. This black hole is not just tearing through space, it is building something. The 200,000 light-year trail behind it is not debris. It is not destruction. It is nurseries. Stars being born, one after another, in the wake of an object that was supposed to be incapable of creating anything. Understanding why requires understanding what the space between galaxies actually contains. Most people picture intergalactic space as pure vacuum. Nothing there at all. But it is not empty. There's an extremely diffuse gas that fills the regions around and between galaxies called the circumgalactic medium. Spread so thin it is essentially invisible under normal conditions. At ordinary speeds, an object moving through it would barely disturb it at all. The gas would flow quietly around it. RBH1 is not moving at ordinary speeds. It is moving faster than the speed of sound in that gas. When you outrun the speed of sound in any medium, the medium cannot get out of the way in time. Gas piles up ahead of the moving object. It compresses. It heats. It forms a wall of superheated material called a bow shock. The same structure that forms as a wedge-shaped wave at the nose of a supersonic aircraft, the same white wall of water at the bow of a fast boat. RBH1 is generating a bow shock at a scale that requires effort to visualize. A wall of compressed superheated gas being pushed ahead of 10 million solar masses moving at nearly 1,000 kilometers per second. And then behind it, the pressure drops. The gas that was compressed and heated suddenly finds itself in the wake. It cools. It clumps under its own gravity. Given tens of millions of years, those clumps grow dense enough in their centers to trigger nuclear fusion. Stars ignite, one after another, strung out behind the black hole in a glowing thread 200,000 light years long. Stars that will never belong to any galaxy. Rogue stars, born in intergalactic space, born out of nothing but the wake of a monster that was thrown out of its home. CT index STIRS 49, turn 1. Van Dockum said, "Something like this has never been seen anywhere in the universe. We think we're seeing a trail of star formation behind this runaway black hole. How did it happen? How do you throw something weighing 10 million times the mass of the sun out of an entire galaxy?" The answer is gravity itself, but gravity operating at the extreme limits of what occurs during galaxy mergers. When galaxies collide and combine, their central supermassive black holes are eventually pulled toward each other and begin a slow gravitational dance. Two massive objects spiraling inward, orbiting each other for potentially millions of years before finally closing the gap. There are two ways this produces a runaway. The first requires three galaxies. If a third galaxy joins the merger, it brings its own supermassive black hole. Three massive objects in close gravitational proximity is an unstable configuration. The mathematics of gravity do not permit it to remain stable. What happens instead is that two of the three form a tight pair and the third is flung outward with the energy transferred from that pairing. A gravitational slingshot operating at the scale of entire galaxies. The ejected black hole leaves with enough speed to escape the gravitational pull of the whole merged system. The second mechanism requires only two black holes and is stranger. When two supermassive black holes finally merge, the event releases an enormous burst of gravitational waves, ripples in space-time itself. If the two black holes have different masses and different spin orientations, those waves are released asymmetrically. More energy goes out in one direction than another. And when energy is released in one direction, the object recoils in the opposite direction. The same principle as a rocket engine applied to the warping of space-time itself. If the mass ratio and spin configuration are asymmetric enough, this recoil kick can exceed 1,000 kilometers per second, enough to send the newly merged black hole flying out of its galaxy and into the intergalactic void forever. In July 2026, a team led by Tusif Islam at UC Santa Barbara published a study in Physical Review Letters that worked this problem backward from RBH1's known speed and trajectory. CT index 46.1. Using numerical relativity simulations, they reconstructed what the original black hole merger must have looked like. Their conclusion, the two original black holes had a mass ratio of no more than 6.1. The larger was spinning with a dimensionless spin of around 0.75, and the binary was precessing, as it spiraled inward before the final merger approximately 70 million years ago. That specific combination of masses and spins produced a gravitational wave recoil powerful enough to launch the remnant at almost 1,000 kilometers per second. Think carefully about what that means. Scientists looked at a glowing streak in Hubble archival data, confirmed it with Webb. measured its speed and geometry, and then ran the physics backward through Einstein's equations to reconstruct the precise spin and mass configuration of two black holes that merged 70 million years ago in a galaxy 8.8 billion light years from Earth. They read the ancient history of a cosmic collision from the wake it left behind. Now here's the part that carries the most weight. RBH1 was only visible because it happened to be flying through a patch of gas dense enough to light up. Site index 37.1. If this same object were moving through a region of sparser intergalactic gas, we'd never know it was there. No bow shock, no star trail, no streak in the Hubble data, nothing. Completely invisible to every telescope currently operating. Galaxies have been merging for over 13 billion years. The conditions that produce runaway supermassive black holes are not rare exotic edge cases. They are natural byproducts of the way galaxies grow. Cite index 39/1. In 2025, several papers showed images of, surprisingly, straight stellar contrails within galaxies, suggesting runaway black holes may be more common than previously assumed. One describes a long straight contrail cutting across NGC 3627, likely caused by a black hole of about 2 million solar masses traveling at 300 kilometers per second, with a contrail around 25,000 light years long. Multiple candidates in a short period, different galaxies, different mass scales, all showing the same signature. The process appears to be real and repeating, which means the question that now sits on every astronomer's desk is not whether more runaway supermassive black holes exist. The question is, how many are out there in the empty spaces between galaxies right now, dark and silent, passing through regions too sparse to light up, sailing through the universe at millions of miles per hour with nothing to mark their passage? We built our model of how galaxies work on the assumption that supermassive black holes stay at the center, that the relationship between a galaxy and its central black hole is permanent. The confirmation of RBH1 does not break that model. The vast majority of supermassive black holes almost certainly do stay put. But it adds a new category of object that nobody had ever confirmed existed outside of theoretical papers. Black holes that got evicted. Black holes that are out there, right now homeless and invisible, having left their host galaxies behind tens or hundreds of millions of years ago. Cite index 37/1. Van Dockum put it plainly, it boggles the mind. The forces needed to dislodge such a massive black hole from its home are enormous. And then there is one more detail that deserves to close this story. RBH1 was found by accident. Someone scrolling through archival images looking for something completely unrelated noticed a straight line that had no business being there. If that person had been looking at a different image that day, this discovery would not have happened. The streak would still be sitting in the archive, unrecognized, waiting. How many more are waiting in archival data right now? And how many are flying through? Regions of space too sparse to leave any mark at all, impossible to find, regardless of how carefully anyone looks. Cite index 37/1. Van Dockum said the obvious next step is to look for more examples. The Nancy Grace Roman Space Telescope, preparing for launch with a field of view 100 times larger than Webb, is the instrument most capable of turning this from one confirmed discovery into a population. The universe may be full of these things. We have found one. We are only just beginning to build the tools to find the rest. And somewhere out there right now, at 2.2 million miles per hour, with a 200,000 light-year ribbon of newborn stars behind it, one of them is still moving. Nothing chasing it, nothing waiting for it, just the dark,